right, so starting recording, we are now on, this is September 20th, this is Physics 1C. Today we're going to be discussing, this is the first hour, today we're going to be discussing the topics that are included up here. We're going to talk about mostly Gauss's law for most of today's class, and then whatever time we have left over, we're going to talk about something called electric potential energy and use that to develop what's called electric potential. Those of you that have already done the lab, E42, might have some idea what electric potential is. But electric potential, we measure it in volts. So probably all of you have heard of a volt before. I'm going to do a brief review of what we discussed at the end of class last time related to Gauss's law. We're going to look at a conceptual example of Gauss's law, and then we're going to look at 3 practical examples that should hopefully help you to do the Gauss's law homework. So let's get started with that. So what did Gauss's law tell us? We learned last time that you can quantify something called electric flux by doing an operation like this. You can do a surface integral of the electric field dot product with something called dA. And dA was a surface element, and it's like an area. Just to remind you, if I have like a sphere, for example, so if I have a sphere here, the dA represents, like if I was to come onto the sphere here and say that I could break up the area of the sphere into a grid. You know, you can obviously overlay a grid onto anything you want to. Suppose that I break this object up into a bunch of equal little pieces, and I say each one of them has an area that we call dA, and it creates a vector that points out of the surface, okay? This is like a surface element. It's a piece of the surface, and it has an area. The area vector is always perpendicular to the surface, and it points out away from surfaces, okay? Always away. So if I chose a piece over here, you'd have a dA vector that would be perpendicular to the surface there, making a right angle to the surface at that point, and that would be a dA over here. If you take the electric field and dot product it with your dA and you sum over your whatever area you want it to use, then you get the flux, and that's defined like that. What we did last time was we calculated the flux created by a point charge. So if you place a positive point charge right here, and it has some charge that we call Q, then it's going to produce electric field lines, and those electric field lines are going to point away from the surface like this. We went through a calculation, and we figured out that if you were to calculate the net flux, the total flux through the surface, then what you get is that the total flux is found by doing this surface integral, okay, over the entire surface. And that's what's represented by this circle right here. You need to evaluate the surface integral over the entire surface. And we found that if you put a positive charge inside of here, that the charge that you place inside of there divided by epsilon naught ends up being equal to this. And this is what Gauss's law states. It states that the flux through a closed surface surrounding a positive point charge or a charge is equal to the size of the charge divided by epsilon naught, okay? This is Gauss's law. Scoot this down just a little bit. So the way that I would write this is the total flux is equal to the charge enclosed divided by epsilon naught. And you have to add up all of the different charges that you have. But when you do that, the net flux ends up being equal to charge enclosed divided by epsilon naught. And if we know what that's equal to, what we can do is that what's meant by a Gaussian surface, a closed surface? No, Patrick, they're not the same thing. Although Gaussian surfaces often will be closed. You'll know more about what a Gaussian surface is here in a little bit. But for now, don't confuse those two ideas. It's a good question. They're different concepts. Okay, so we have this. I guess all Gaussian surfaces are closed surfaces, but not all closed surfaces would be Gaussian surfaces, is what I would say. Anyway, So we have this definition right here. But the thing is that's interesting about this is that this is also equal to this expression. And this is how we're going to use Gauss's law. Usually the way we're going to use Gauss's law is we're going to start from this relationship. So this is often how we're actually going to apply Gauss's law. But all of the things that are in boxes here are Gauss's law. Just keep that in mind. Every one of them is Gauss's law, okay? Gauss's law says something about flux. It says the net flux through a closed surface, is Q enclosed over epsilon naught. But it also relates that to the integral of E dot dA. So we use Gauss's law to solve for electric fields, okay? That's the main thing we're going to use Gauss's law for. It's not the first thing we're going to start using it for, but this is the main thing we're going to use Gauss's law for. It's going to allow us to describe static electric fields given certain distributions of charges. But what we're going to do first, in order to kind of pound home the concepts of what flux is and how it relates to point charges, we're going to do a conceptual example. Okay? But you need to keep in mind all these things that are written up here. Mostly just the statement here. The flux through a closed surface surrounding a charge or group of charges is equal to the charge enclosed divided by epsilon naught. Okay? So let's look at what this says. It says, a spherical Gaussian surface surrounds a point charge Q. Describe what happens to the total flux through the surface if the charge is tripled, the radius of the sphere is doubled, the surface is changed to a cube, and if the charge is moved to another location inside the surface. So we have a spherical Gaussian surface. Don't worry about that word Gaussian. It's just a spherical surface. That's all that you really need to know about that. So let's draw a sphere. Oops. Hey, let me grab the edge. There we go. So here's our sphere. And what it says is that we have a charge inside of this. So we'll put a charge inside of here. Positive charge. It doesn't actually tell us where the charge is, but I'm going to put the charge kind of near the center here, okay? So this is going to produce some flux, right? And it produces flux because there are electric field lines that emanate out from this charge, right? Electric field lines that look something like this. And anytime you have electric field lines that are emanating from a charge, those field lines are going to create a flux through the surface, okay? So these are all electric field lines. We'll put arrows indicating the directions that they're going. These are not electric field vectors, they're just lines that are tangent to the electric field at every point. So there's our electric field lines. There's our surface. And I tell you the charge has a size point Q, or just Q, that's inside of it, and we give you the surface here, and let's say that the surface has a radius. Let's put a radius on here. So the radius of our surface here is going to be little r. What is the flux through this surface? What's the total flux through this surface equal to? Is it the electric field times pi r squared? Maybe, but we don't really know what the electric field is right now. I just tell you I have a surface, I put one charge inside of it. Yeah, Elijah has the right answer. It's Q, the size of the charge, divided by epsilon naught. That's the answer. For example, if we chose Q to be 9 nanocoulombs, right? Let's say we chose Q to be 9 nanocoulombs. This would be equal to 9 times 10 to the 9. That's in newtons divided by, it's Newton meters squared over coulomb squared. What am I doing? No. That's K. What am I doing? Losing my mind. Q. Let's say Q is 9 nanocoulombs. That would be 9 times 10 to the negative 9 coulombs, right? You divide by epsilon naught, which is a number, right? It's 8.85 times 10 to the negative 12, and then it's coulombs squared over Newton times meter squared. if you plug all these in together, you're going to get about 1,000, a little more, probably like 1,200, I think. Okay, I got actually 1,000. Do you all agree? You get 1,000 if you do this? Something like 1,017 or so. You approximately get 1,000. Do you all agree? Okay, so that's our flux right there. Now, I know a lot of you answered something related to the electric field and the radius squared and stuff like that, but understand that if I have a closed surface here, which is the sphere, and I want to find the flux through my sphere, the answer is just the charge inside divided by epsilon naught, okay? This is like part 0 of the problem. We haven't even done part A. The question is, what happens to the total flux through the surface if the charge is tripled, right? So for part A, Q goes to 3Q. What happens to the flux? Does it get cut in third? Does it triple? Does it stay the same? What happens? It triples, right? That should be pretty obvious. This should go to 3 times whatever our original flux was. Okay? Which means in this case, our new flux is now equal to about 3,000 newtons per coulomb. Okay? So that tells you that if I have, so part A, so that was our initial setup, right? For part A, what we have is, now we have 3Q surrounded by a sphere, and the answer is that now the flux becomes triple the flux. Okay? So that was the first part. This is part A. Charge triples. Oh, I messed up. Sorry. The units for this, I messed up right here. The units for this first one, this should have been, I'll put it in a different color. This should have been Newton meters squared per coulomb, newtons meters squared per coulomb. There we go. That's the units we use for flux. I think this unit is called a Weber too. Don't quote me on that though. Maybe right or maybe wrong. I can't remember. All right, part B says, what happens if the radius of the sphere is doubled? So let's do a different color. What happens if I take my same object and I double the radius of the sphere? So now, draw a little different picture. So now what we have is bigger sphere, has radius 3r, and inside we go back to our original charge. So it's just charge Q now. The flux is unchanged, okay? So now what happens is we realize that flux is only dependent upon the charge inside, and if you make the radius bigger, you don't change the flux, right? Okay, so same flux. So that means that the flux is now going to be the same as what we had in part A, or part 0, whatever you want to call this up here, which is 1,000 newtons meters squared over coulombs. So by changing the shape of the Gaussian surface, okay, by changing the shape of this closed surface, the flux doesn't change. Okay. Okay, part C. What if the surface is changed to a cube? So in C now we have a cube. That's our closed surface, or Gaussian surface if you want. And now we still have a charge inside of here. It's the same charge from the original part, which was Q. So now again, yeah, like you all are saying, same flux, because we changed the surface, but we didn't change what was inside of it, which is all that really matters. So again, the flux in this case would be equal to the same as before, 1,000 newtons meters squared over coulombs. Okay, and then in part D it says the charge is moved to another location inside the surface. So it stays inside the surface, but it's now in a different location. So what that's going to look like, let's go part D right here, is now here's our surface, okay? And let's say that now, instead of it being right at the center, we place our charge somewhere over here on the edge. What's that going to do? Is that going to change the flux? No, it's not going to change it exactly. Again, the same flux. So what was the only thing that we were able to do to actually change the flux in this case? What was the only thing we did? Yeah, you have to change the charge. If you don't change the amount of charge that's inside, you don't change the flux, basically. It's only by changing the charge that you change the flux. Now I want to go back through here and say some things about electric field lines and why this ends up working out, okay? So previously I drew a total of 8 electric field lines coming out right here, right? I just want to emphasize, how things change right here. So if we have 3R, right, and I use the same definition for my electric field lines, that is to say that I draw 8 electric field lines out of here. So 1, 2, 3, 4, 5, 6, 7, 8. The thing is that one of the reasons you could say that the flux remains unchanged is that there's still 8 lines of flux that are leaving, right? 8 electric field lines that are leaving, right? If the number of lines doesn't change, the flux also doesn't change, right? So that's why here, when you have this surface, you could still, have the exact same number of lines. Now, what about the 3Q, though? It's the only one that was different. What am I supposed to do with my electric field lines when I have triple the charge? What does that mean is going to have to happen to the number of lines that I draw coming out of the surface? I have to draw 3 times as many lines, right? So I'd have to draw 24 lines. I'm not going to draw 24 lines on here, but you'd have 1, 2, 3, 4, 5, 6, 7, 8, and everywhere in between here, you're going to have to add 2 lines, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, and now we have more lines. It looks terrible, but this was the 3Q picture, by the way, just in case. This is 3Q right there on the inside. Okay. So let's see if we can continue through this and see what happens. Obviously, this one's same deal, right? If I draw 8 lines coming out of this, still all 8 lines are going to leave, right? But what happens if I move the charge outside the box, right? So what if I take my sphere? So let's say that we're using, again, let's say we use a Gaussian surface here. This is our surface. It's a closed surface, so it's a sphere or something like that, right? So what happens now if I put my charge over here? So now what happens is, as I'm drawing my electric field lines, right? And I'm just going to draw the lines that are like nearby the surface, okay? But there's more, obviously. We can keep drawing electric field lines, right? Now what happens is that every time a line enters my surface, you get negative flux. Remember that? When a line goes into a surface, it's negative flux. And when it comes back out the surface, it's positive flux. So negative flux here, positive flux here, negative flux here, positive flux here. And it ends up canceling out. And so in this case, the net flux is equal to 0 because every line that comes in also comes out. Again, you can conceptually understand flux by thinking about field lines, and the number of field lines, okay, crossing the surface is directly proportional to the flux. So if you just count lines, then you can find the flux, basically, right? That's why I set up here that if there's 8 lines out here and I make the object 3 times as big, you're still going to have 8 lines because they're all going to go out forever. When the object has no charge inside, in this case the net flux is 0 because any line that enters on the left side also goes out on the right side. So it's like, any line that comes in also goes out, then you're going to get a net flux of 0. Okay, does that make sense? This is all just basically a review of what we did last time with some extra details that I'm adding in. You'll have a good understanding of what electric flux is. All right.
Professor, may I, real quick?
Yep.
Just mathematically, that's because going in, the way you drew it, going in, the cosine of the angle there would be like cosine of 180, and that would be -1.
Yeah.
And that's why it's negative going in, the way you drew it in the diagram there.
Yep. So if I drew my surface element here, you're exactly right. This dA would point this way, whereas the electric field, obviously, at that point is going this way. And yeah, so then the angle between the two of them is 180. So when you do cosine 180, you get a negative sign. So this is negative flux on the left and positive flux on the right. Exactly. Okay, does that make sense to everyone? That's a good question. Okay, so now let's get into the kind of more nitty-gritty of Gauss's law, and let's look at some problems that we can solve using it. Okay, And the first one is going to be right here. Now I'm going to give you a little bit of an intro to solving Gauss's problems before I put it in here. We'll paste this down here. Feel free to look at the problem if you want to. It's a pretty short problem. I mean, the words are short. The problem itself is pretty long. So, solving. Ugh, I hate writing on this thing so much. Solving Gauss's law problems. Okay, so what you do with Gauss's law problems in order to solve them is step 1, draw field lines. Electric field lines. Step 2, choose a surface. Choose what we're going to call a Gaussian surface. It'll be a closed surface. It has to be a closed surface, okay? Can't be an open surface. And the way that you're going to do this, you're going to choose a Gaussian surface such that the surface itself is parallel or perpendicular to your field lines. Does that make sense? It'll make a lot more sense when we actually do it. But we've already done one, so we can use that as an example. Like, if I chose a positive charge, step 1 would be draw field lines, right? And step 2 is to come up with a surface such that all of these field lines are either perpendicular or parallel to the surface. Now, keeping in mind that for a point charge, the field lines are going to come out radially in all directions, then you could say that for a point charge, there's a type of spherical symmetry that's going on. And in order to create a surface that is perpendicular at every point to those field lines, well, there's really only one possibility, and that's a sphere. There's no way to make a surface that's going to be parallel to the field lines. Wow, it's just not going to respond to my interactions with it. I love it when this happens. Click this, is it red? Nope. What's going on right here? Why can't I make it red? This seems to be selected somehow, I don't know why. Red? Red? Okay, I don't understand why this thing doesn't work sometimes, but okay. So, the point is that if these are the field lines, right? If these are the electric field lines, you're going to want to choose a surface such that the field lines will always make a right angle with the surface. And the only way to do that is to draw a sphere. If I chose instead to draw a cube, right? So if we take the same setup here and look at what happens if we choose a cube instead. So get rid of this right here. We want to choose a Gaussian surface that surface is parallel or perpendicular to the field line. So I'm drawing in this field line that I erased by accident. So if that we have that field line. If instead I draw a box around this, right? And then I imagine that I put a cube here. We're just doing two-dimensional stuff to keep things simple. Now what's going to happen is that some of the field lines will be at right angles, right? That's at a right angle, that's at a right angle, that's at a right angle, and this is a right angle. So that's good. Now if all the other points are parallel or perpendicular, we're good, but they're not, right? This is not a right angle, this is not a right angle, and this is not a right angle, and this is not a right angle either. That means that this is a bad choice. This tells us that a cube is a bad choice for a point charge. It may be a good choice for other possibilities. It will be a good choice for other possibilities. We will see that later on. But for now, we can see that this would be a bad choice. Okay? All right, just to be really clear here, these things are what we're calling the Gaussian surface. It's the surface that you surround the system with. Okay, so step 1 for solving Gauss's law problems is to draw the field lines. We did that. Step 2 is to choose a Gaussian surface, closed surface, such that the surface is a parallel or perpendicular to the field lines everywhere. Okay, so can you see why a sphere would fit that definition, but a cube would not. Can everyone see that? Does anyone have any questions? Okay. Good. Now, doing these problems can be very challenging, but if you take the time to do things properly, they will be very easy. It will be challenging, but doable, okay? The last step in this right here is to use integral of E dot dA is equal to charge enclosed divided by epsilon naught to find the electric field. This is ultimately your goal, okay? This is ultimately what you're trying to do in Gauss's law problems, is you're trying to find the value of the electric field. So you apply Gauss's law right at the very end, okay? This is the part where you use Gauss's law. But just like in physics 1a, where unless you're just a really bad student, you don't just start with F equals ma when you do force problems, right? You do those force problems by drawing a free body diagram, labeling axes, indicating certain points that might be interested, and then you might use F equals ma, but you don't even really use F equals ma, right? You use net force in the y direction equals to may, net force in the x direction equals to max, and you go from there, right? There's an algorithm that you go through that helps you to solve this kind of problems. This is the same way. So if you're just immediately starting these problems by using this equation, that's equivalent to trying to solve problems in physics 1a by jumping immediately to F equals ma, right? You need to do these first two parts first. Gauss's law problems are geometrical problems. I cannot emphasize this enough. The last time I taught this class, I had so many people that turned in their lab manual problems and they didn't include diagrams with any of their Gauss's law problems. There was no diagram. They just started by doing math. They started from this equation and assumed that I could just follow it. As I go through Gauss's law problems today, I'm not drawing pictures because I feel like it. I'm doing it because this is what I expect you to do. So pay attention, and you have to do these things if you want to get credit for the Gauss's law problems that are on your homework, okay? That goes for an exam too. So you have to draw the picture. You have to draw the Gaussian surface. You also need to do things that I'll show you. I'm not going to write every single step that I'm going to do down here, but you're also going to have to include the direction of the dA vector as well, and that's how you're going to use this. So given those steps, let us look at some problems that we can solve. This first one is called a cylindrically symmetric charge distribution. It says, find the electric field a distance r from a line of positive charge of infinite length that has constant charge per unit length, lambda. Is that straight? I really can't tell. Maybe it is. Looks pretty straight. All right, so we have our line. It is a positively charged line of infinite length. So let's indicate that it's positive here. Just go along here and say this is positive. And what we know is that it is uniformly charged, which means it has equal charges per unit length. And the charge per unit length is given by the quantity lambda. Remember, lambda is, charge per unit length. Okay. So we've drawn our picture of the object, which is an infinite line charge. That's what I would call this one. Infinite line charge. Now, I've drawn that. Step one for solving Gauss's law is to draw the field lines. Now with this, you have to use your imagination because sometimes you're not exactly going to know how the field lines are going to point, but you can kind of tend to figure it out. In this particular case, maybe someone can tell me, what are the electric field lines going to look like for this object? What are they going to look like? It's a single line of charge. Should I draw my electric field lines pointing like this? Should I draw them pointing away like this? Should I draw it pointing towards it? Should I draw it start pointing up, moving away, okay? And you say that because you know that this is a positively charged object, right? So that means that the electric field line should point away from positive charges. So let's draw some field lines in here. Copy, paste, click, copy, paste. Paste, 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 paste. So we're going to have a bunch of field lines like this. And let's spread them out. Oops. Spread them out a little bit. Okay, you don't need to draw excessive numbers of field lines like I'm doing. You just need to sketch in general what they look like. But I'm actually going to draw them because this is a geometrical kind of thing, and I want to make sure everybody's learning how to do it right the first time, I guess I would say. Okay, now these field lines are going to continue forever. So if I really want to, what I would need to do is somehow select all of these without selecting the positive signs. I don't think I can really do it. But, yeah, I can't really do it. That's okay. They go on forever is the point. Can I switch it around this way? No, I can't. I want to draw them on the other side too. Right, well, let's just say that you understand that these lines are going to go up and down forever like this, okay? And then on the other side, we're going to have the same image. What I'd like to do maybe I can do this. Copy, paste. Can I invert it somehow? This is whatever. I'm just going to pre-draw. I don't know what else I can do. Okay, opposite side, you're going to get the same kind of thing. You're going to have electric field lines over here. I'll just draw one for everyone that's here. These field lines basically extend forever too. They don't really stop, but I'll just draw them out to there. All right, copy, paste. Oh, I know what I could have done. No, it doesn't let you do that. That's interesting. Okay. Shift? No. Okay, so we get all our field lines. And the next thing that I need to do is think about the three-dimensional nature of these field lines. So these field lines are not just going to be in the plane of the page. Where else can I draw them? Where else could I draw these field lines? Out of the page, yeah? Into the page, right? At angles away, too, right? I can have field lines kind of coming out this way, going in this way, right? So up here, what I'm going to do is I'm going to look at a top-down view. And say from the top-down perspective, what we have is we've got our positive charge in the middle here. Let's use the same color. It really sucks that the undo button's not working. So the top-down view would look something like this. We would have our electric field lines coming out like this. And then just going into the page, right? So it is a cylindrically symmetric charge distribution. Maybe you can see why now. The field lines kind of cylindrically point out away from the object, right? And all I'm showing here is basically just like a cutout of, yeah, but the reality is, yeah, the lines come out this way, they come out this way, they come straight out, they go back this way, they go back this way, and they go straight on the page. I'm going to erase all those lines, but does that make sense to everyone? You could think of like maybe drawing 8 field lines here that are in the plane of the page, all pointing away from your object, right? Okay. This time Control-Z does work. Okay, so the next thing you have to do, now that we have an idea of the field lines, right? We did number 1. We've already done this one. Is so now we need to choose a Gaussian surface such that the surface is parallel or perpendicular to the field lines everywhere, right? So I can make my surface parallel or perpendicular to the field lines, and I got to choose something. So what would you choose? What kind of surface can I place in this region here? A cylinder. Yeah, that's the answer. It's a cylinder. Because, okay, let's talk about this. Why can't I put a, let's say, a rectangular prism around this? Why can't I come in here and draw a rectangle around here? Why can't we do that? Why would that not work? The perpendicular thing. Well, these look like they're perpendicular. These are all perpendicular. And the top surface looks like it's parallel. What's the problem? Yeah, that's right. If we come to the top-down view over here, if we did in fact put a rectangular prism inside of here, when we look down from the top, what we would see, what we would see if we look down from the top is this. And now these lines are going at different angles. And so as a result, we know, when we look at the top-down view, we know that the cutout on top at the very least needs to look like a circle, right? Because everything is cylindrical. We know that our Gaussian surface on top has to look something like that. And the only way to put together the nature of the prism that goes down, that produces the lines that are perpendicular here and here, is to replace it with a cylinder. So our Gaussian surface in this case is going to be a cylinder. I will draw it in here. So that's going to be the top of our cylinder. Draw it a little bit bigger. Stop it. Jesus, this is goddamn hard. Okay. We come down to here. We need to have the lines on the edges connect up. Like that. And like this. Hopefully those will line up okay. They did. Okay. So that is now our Gaussian surface, drawn on the top and the bottom. Gaussian surface. I will often just refer to it as a Gaussian, although I think it's probably bad. Okay, so we look along our surface here, right? And now I'm gonna tell you some things that aren't in the list of what you do. The next thing you need to do is you also need to draw your dA at every point. Okay, we'll call this step 2 prime. Okay, so whoops. We'll call this step 2 prime. So this is the next step. You have to draw dA at each surface showing the angle between the electric field and dA. So what I'm going to do is I'm going to come, for example, to this point right here and say it's a curved surface. I know that the direction of the area vector there is going to point away from my surface, so that's going to be my dA. The green lines here was the electric field. So here we can see that the angle between dA and E is 0. Would you all agree? And that same idea is going to be true on the left-hand side over here, that dA is going to point away like that. The electric field at that location is pointing, as you can see, to the left. So again, we have the angle between E and dA is 0, which is good. What about the top surface? If we come to the top surface up here, what we're going to see is, well, you all tell me, what direction is the area vector dA going to point for this top surface up here? Does it go up or down? When you have a flat surface, it's basically either up or down, but I gave you a rule. What's the rule when you have a closed surface, when you could choose either up or down? Why do we know it's up? Maybe you don't remember. We did it on Friday, or the last time we talked, which would have been Wednesday. Outside the shape, exactly, that's right, Evan. It's always going to be that it points away from the surface. Okay, so that's dA. And of course, here was my electric field. What I'm going to do here is I'm going to draw another arrow right here just to indicate that that's electric field, to be really clear. So my electric field vector at that point is going to go this way. And now we have a situation where the angle between the two of them is 90 degrees. So another way that I could have set this all up for you is I said to make sure that choose the Gaussian surface such that the surface is either parallel or perpendicular to the field lines. When the surface is like this, I would say the surface itself is perpendicular to the field line. But another way of saying that is you could say you want to make dA and E have an angle of 0 between them, or these need to be parallel. E and dA need to be parallel, or dA and E need to be parallel. Perpendicular, like on the top right here. Okay, so we're done. We could also draw the same thing down here. I'll just draw it freehand. You also have a dA vector that comes out this way, right? And it will also make an angle of 90 degrees. So we're all set. Now, once you've done this, the next 2 steps, I always feel like when I was studying this, always felt like magic, because I often didn't quite understand the steps that were being made, and so I kind of had to just follow them blindly as if it was like a magic trick. So I want to emphasize this next part is, it's either going to be very easy for you or it's going to be very confusing what I do next. So if you have any questions, please pay attention carefully to what we do, and please ask. If you have questions about what I've done before this, you can ask those too now by typing in the chat. So step 3 says to use E dot dA equal to Q enclosed to find the size of the electric field. That's what we're going to do, okay? And there's some subtleties to this. So you start off with the equation, as we often do. You start with this for doing step 3. We know this is equal to Q enclosed over epsilon naught. But immediately, we realize that Q enclosed is no longer as simple as it was before. Previously, we were just looking at like a single charge inside of an object. We could have talked about what happens if you put multiple charges in there, but that's really no different than adding up charges. Maybe we should have talked about that, but in this particular case, the charge enclosed is going to be equivalent to how much ever charge actually exists within this region right here. Now, in order to define what that is, I need to know something about my cylinder. So in this case, I'm going to say that the length of my cylinder is L, and we'll say the radius of the cylinder is R. The radius is R. Okay? So the length of my cylinder is L and the radius is R. What I want you all to think about right now, while I'm going to work on the left-hand side of the equation. I want you to think about what this is going to be equal to. I don't want you to type in the chat, I just want you to think about it. Try to figure out for yourselves what this is going to be equal to in this problem. And it's going to be, gotta maybe reread what's up here. Okay, the left-hand side, though, we can do. And the left-hand side of these type of problems is going to be the same every single time. This one's a little bit different, but what I'm going to do is I'm going to say that I need to perform this evaluation over the entire surface of the object. But I realize that my object is really made of 3 different surfaces, okay? It has a curved surface, it has the top surface, and it has the bottom surface. And I need to do this E dot dA surface integral over each of them. And it's usually easier to do so if you separate it out into pieces. So what I'm going to say here is that this is going to break down into the flux through the curved portion plus the flux through the top plus the flux through the bottom. And all of these will end up being equal to Q enclosed over epsilon naught. And again, I want you to be thinking about, as I'm doing this, I want you to be thinking about for yourself, what will this be equal to? All right. Flux through the curved surface. So are we finding like volume? No, we're not finding volume. We're solving for the electric field. That's what we're doing. We're solving for the electric field. This is what we're trying to pull this out of the integral, basically. This E. Okay. So this breaks down into flux through the curved portion, flux through the top, plus flux through the bottom. Top and bottom are going to be 0, yeah. Let's do the curved part first. Now, what do we notice with the curved part? What we notice is that the integral of E dot dA, all right, this is just for the curved part. What's the angle between E and dA? God, every time I try to write so small, it's just completely illegible. And if I write, it's so hard to write small with this. It's really frustrating because it reorganizes and reworks it. The angle between E and dA is 0, right? So what we can do with our integral right here, our integral now, we can write it as just E dA cosine of the angle between the two of them, which is 0 degrees, right? And the cool thing we can do with this is we can get rid of these vector symbols, which makes this a lot simpler. I'm still working just on the curved portion, by the way, so I'm just going to keep writing curved down here to indicate we're just performing this integral over the curved portion, right? The next thing we can do, and this almost always will happen in these problems, not always, but almost always you can do this. When I think about what's happening in this problem, and I think the best way to look at this is to look back to the Gaussian from the top-down view. What can I say about the value of the electric field, let's say right here, compared to the value of the electric field here, if I'm assuming that the line is right at the center of my cylinder? The value of the electric field here, 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 all along that surface. What do I know about the value of the electric field there? I don't know what it is, right? But how can I relate the electric field on here? They're all the same. It's all constant, yeah. It's all the same, exactly. So what I can do then is I can say if every portion of my surface, we're integrating over dA, right? So that says come to every part on your surface right here and evaluate what EDA is equal to, right? But because of the cylindrical symmetry, if I stay the same distance r away, then the E is not going to change. And when the electric field is the same at every point on your surface dA, you can just pull it out of the integral. So that now you write the integral over the curved portion, over the curved surface of dA, cos 0 is obviously 1. We get that. And then the next step is this says to sum up every area element of the curved surface, which means basically tell me what this right here is going to be equal to the surface area of the curved part of the cylinder. That's what this is going to be. This says find the area of the curved part of the cylinder, which is just circumference times height. That's exactly right. So in our case, that is going to be equivalent to 2 pi r times the length of the cylinder. And to me, why was cosine 0 again, Copy? So when I say E dot dA, what I mean is I take E times dA and I take the cosine of the angle between the two of them, right? Just as a brief refresher, if this is E and this is dA and this angle is theta, then is that being shown on the screen? I hope it is. Then E dot dA is defined as EDA cosine of theta. Does that seem familiar to you, Copy? This is the definition of the dot product, and if you don't remember it, it may be a good idea to go back and review the dot product. We call this dot product. Okay, and dot product would be covered in your physics textbooks, also in your calculus textbooks, like if you took vector calculus, but of course you can just look it up on the internet too. In my humble opinion, the development that's in your math book is probably more complicated than you really need to understand what we're doing here. So probably better to just look at a physics textbook. It's going to keep things simple. Okay, so there's really 4 pieces to this equation, right? Going back to what we were doing. The flux through the curve plus the flux through the top plus the flux through the bottom is going to give me the flux through my whole surface. So we've just done one part of that, right? We also need to write in here what the flux through the top and bottom are going to be. Someone already said they're 0, and they are correct, but let's see why. So now what we're going to be doing is, through the top surface, we're going to be evaluating E dot dA. But what's the angle between E and dA on the top? It's 90, so we multiply this by cosine 90, but that is equal to 0, right? And for the same reason, the flux through the bottom is also going to be 0, okay? Is everyone following along? So can you see, just let's stop for a second and understand. Can you see why it was so valuable that the angle between E and dA here be a right angle? Sorry, oops, my bad. This is the one where it's 0. This angle is 0. The angle between E and dA is 0 here. The angle between E and dA over here is also 0. They're parallel vectors. But on the top and bottom, the angle was 90, which meant that they contributed nothing to the overall calculation of the flux. That's the reason why step 2 exists. Choose a Gaussian surface such that the surface is parallel or perpendicular to the field lines. It allows us to vastly simplify doing this integral, right? To just turn it into E to EDA cos theta. Now we have just scalars. And then very commonly what we end up doing is we just pull the E out of the equation because the electric field is uniform over the surface of the object that we're looking at. Okay, so here's the part that I asked you to calculate and think about yourselves. The right-hand side. Can you explain again why you can take E outside the integral? The reason why is because if I look at any point on my surface right here, there's so much symmetry in this problem, right, that the electric field has to be the same at every point on the curved surface. After all, every point on the curved surface, how far, okay, so the radius of my sphere is r, right, keep that in mind. How far is this point away from the object? Away from the, it's r, right? And if I choose any other point on the surface of the sphere, you would agree the same distance, r, right? So isn't it reasonable to assume that the electric field at that same distance r away should be the same anywhere on the object? Would you agree with that statement? The electric field should be the same everywhere. It's not going to be the same if I come to some position like, let's say here. If I come to a position of like r over 2, what's going to happen to the electric field? If I come to a position that's like half of the radius, somewhere in here, and I ask, what's the electric field here? Would you all agree that it has to be, at the very least, it has to be twice as big? Maybe 4 times as big? If you get closer, it really has to get bigger, right? But if you stay the same distance away, it doesn't. You could stay all along that surface, you have the exact same thing. And so that allows us to do this. And this is what I was saying at the very beginning when I first started doing these problems, Tombui, was that this stuff felt like magic to me. Because I was like, well, how do I know I can do this? Like, how do you know you can just pop this out every time? And you kind of have to use your knowledge of what we've learned prior to this about electric fields and charges and how they interact with each other. And part of it is you have to just think about the geometry of the problem. And very commonly, the geometry will tell you that you can just do this. In fact, that's really your goal. You're never going to do this integral in this class. I always find it so funny when people say, oh, you need to take 220 to take this course. And yeah, it definitely helps. 100% it helps. But the reality is we're not really doing a surface integral here. We are, but we're not really, we're not following through the details of how you do a surface integral that you use in 220. We're literally just shortcutting it because we can. Because what we're doing is we're not just calculating a surface integral, we're trying to find electric fields, and that involves choosing a Gaussian surface through which we will do a surface integral. But when you can choose the surface, you can purposely make it so that the electric field is the same everywhere on your surface. And you will always do that with these problems, you'll see. We will always be able to do this. If you do it right, you can always make this move, okay? So it's allowed. You just need to show the steps to how you get up to it. Okay. So, getting back to the question that I asked you, the right-hand side of the equation, that's the other piece of this, right? How am I going to find the charge enclosed? We'll have to take a break right after we finish this one. Did anyone figure it out? What is the amount of charge that has been enclosed by my Gaussian surface? Now, keep in mind, I don't know how to highlight this on here. Maybe I'll use yellow. If I look in this region right here, right? How much charge is actually there? And Tombui is correct. The amount of charge that's actually enclosed by my Gaussian surface, Q enclosed, is equal to the charge per unit length, lambda. That's, lambda could be, for example, 20 coulombs per meter. And I tell you the length of this is 1 meter. How many coulombs are in there? It would be lambda times the length. That's what charge enclosed is going to be. Again, just as an example, if lambda is, let's say, 20 coulombs per meter, right? And I tell you that L is 2 meters long, right? The length of this is 2 meters long. If I know that there's 20 coulombs per every meter, then the total charge, right, would just be 20 times 2, or 40 coulombs. If we make the length of our cylinder twice as big, if we make it like 4 meters long, you would enclose 80 coulombs of charge. And how do you do that? Well, you take lambda and you multiply times L. Does that make sense to you all? If it's hard to understand, you can replace coulombs with grams. And you could say, suppose I have a string. Okay, so take a string. And I tell you the string has 20 grams per meter, right? And you cut off 2 meters of string. Well, that better have 40 grams in it, right? If it's 20 grams per meter and I cut off 2 meters of it, it's going to be 40 grams. So again, if the coulomb part is throwing you off, it just means that there's, a few trillions of billions of electrons in there that are missing. Okay, so we figured out what's put on the right-hand side. Let's go through and complete the problem now. On the right-hand side, what we have now is lambda times L, that's what Q enclosed is, divided by epsilon naught. And that's basically going to be what the right-hand side states as we go down here. Took a lot more steps for the other side. And then we get down to here. Okay, we still haven't gotten to the part where the chat's blocking. And now we just finished the problem. Our goal, after all, was to find what the electric field is. So our final line here, what we can say is E times 2 pi RL is equal to lambda L over epsilon naught. And now we can cancel out the L's. This will almost always happen. If you have a dimension in your problem that you were free to choose to be some other thing, it will very commonly cancel out. It kind of has to. Or else this what we're doing wouldn't make any sense. After all, if I chose a length L that was 10 meters, and let's say that Jasmine did the same problem and she chose a length L that was 20 meters, the idea of Gauss's law is that we should both get the same answer no matter what we choose for our length, right? And we're seeing that that does cancel out here. So that's good. We're solving for E, so let's isolate E. So E now is equal to lambda over 2 pi epsilon naught times R. This is something that we derived previously. And while what we did right now may seem more complicated now, that's mostly because I showed way more steps than I really needed to make sure that you understood exactly individually what was happening. And the reality is this is a much easier way to get to this result than what we did before. What we did before involved drawing vectors and doing integrals that we actually had to do the integral. And the integrals were quite challenging. Some of them you have to look up in a like the first problem on your lab annual homework where we did a long straight line and you probably had to look up the integral in an integral table. So the value of using Gauss's laws, we can kind of circumvent that and get answers like this. So this tells us that the electric field is the charge density. So the more charge density you have, the bigger the field's going to be, divided by some constants, and then R. This tells us that the farther we get away, the field's going to be weaker, right? And in fact, what I said earlier was that if you came to a position here, R over 2, away, we now know what the electric field at that location is. Something that is very subtle about Gauss's law. I copy this so we can kind of put it up here so we can talk about this. One of the things that's very subtle about Gauss's law, I don't understand how this program works at all. I've been using it now for so much time, and usually by now I figure these things out, but this thing does stuff that's so weird. Okay. So Gauss's law allowed us to find the electric field here. That's what it did. That's what we've done. We've found what the value of the electric field is all along every point, like this point right here, this point right here, this point right here, this point right here. But because we use R as a variable, that means that we could reduce R to R over 2, and we also know what the electric field at this point is. We could say conceptually that it's about twice as big as the electric field out here, because it looks like the electric field is inversely proportional to the radius. But that is what we've done. So we introduced the concept of flux last week. Flux is something that is important to understanding Gauss's law because after all, this is flux. And if you're going to break it up, it's flux through each piece, right? But in reality, Gauss's law is about coming up with an alternative way to find electric fields other than the integration method we learned in the last chapter. That's what we're trying to do. And the answer you get is not specific to your particular picture because R is a variable. And, we could have made our Gaussian, bigger. We could have made it bigger if we wanted to. But the result is general, and that's what the answer is. We could also add into this, if we want to make this even more, if we want to make it into a vector, what we would do is we would throw an R hat on there, right? Because this is a radially pointing out field. So this would be the complete version. Now, does anyone have any questions? And then we'll take a break. The Gaussian surface is imaginary. That's right, Josh. It is just a tool that you use. You draw this thing around your system, and it guides you through doing the integration over here, which in the reality is, as you saw, you don't really do the integral, right? You don't really do the integral. That doesn't mean that you can't. It doesn't mean that this isn't possible to be done with integration. It just means that Gauss's law helps you to do it without having to actually do the integral, which is really quite nice. Because surface integrals are hard. Those of you that took 220, they're not easy, right? When you have to actually do the integral and you've got multiple different limits and you've got to figure out the shape of your surface and all these kind of things. It's hard. So it's nice having this trick that we can use. And as you'll see with what we do today, you can kind of always do it. Okay, I see a lot of people typing. I want to take a break, but I want to make sure. How do we know how to use Gauss's law or the methods we learned in the previous lectures? That's a great question. The answer is, Ton, it's not the simplest answer, but when you have a lot of symmetry in the problem, that's when you can use Gauss's law. When you have a lot of symmetry. I know that's not the best answer, but I'll put it another way. I think you're going to know after having done a few problems, because if you try to use Gauss's law for a problem that it won't work on, it'll become very, very apparent that you will not be able to do number 2. Let me give you a quick example. I really do want to go on break, but let me give you a quick example. If you have a dipole Okay. Remember that the electric field for the dipole looks something like this. I won't draw the best version of this, but I'm going to try. The electric field of the dipole looks something like this. Okay, something like this. I know this isn't a great picture, but just do my best. So now, remember that the second step on what it said was you need to draw some type of a shape around this system, right? You need to draw some type of a shape, maybe a circle, a sphere, maybe a box. And it has to have the features that we described, which is this box needs to either be perpendicular or parallel at every single point, right? Can you see how that's really hard with this type of a charge distribution? I mean, I could imagine that if I drew one like this, that all of the bottom points down here might actually make it so that the electric field lines are, in fact, you know, perpendicular all along the bottom. But then these ones at the top, it's not going to work anymore. Well, maybe this one, but not these. Do you see the problem, Tom? It's very difficult to make it so that the surface is always at the same angles. And so this kind of a problem, if you want to find the electric field of a dipole, let's say the problem says find the electric field of a dipole right here. You have a problem like this in your homework. It says find the electric field of the dipole like right here. I mean, you're going to have to use the method we used before, which means you're going to need to draw a line from here to here. You're going to need to draw a line from here to here. You're going to need to call this one R plus, call this one R minus or whatever, and then go about like, you know, drawing electric field lines. This is going to go this way. That one's going to kind of go off that way. That's the best way to answer. Is just like you'll know very quickly if you can do number 2 or not. And when will you be able to use number 2, the Gauss for this list here? You're only going to be able to do it whenever it's there's some kind of symmetry going on. Okay. All right, let's take a break until 30 after, I think, right? That's 9 minutes. That should do fine.